Welcome back. Now that we spent a lot of time talking about magnetic fields, let's take what we've learned about magnetic fields and apply them to some problems using circuits. But first, let's try to take what we know about solenoids, which is a great object used to create a homogeneous magnetic field, and see what happens when I put that solenoid into a circuit. So consider just the solenoid with some current flowing through it, I, and I'm going to make the current flow through it so that my magnetic field inside the solenoid is pointing to the right with some magnitude given by mu naught times n times I, where this n, this little n, is the number of turns per unit length. Now, we spent some time deriving this formula for the magnetic field inside a solenoid, but now let's actually use it. Because in addition to generating the magnetic field, this solenoid is in fact a bunch of different wire loops. And therefore, if I have a bunch of wire loops with a magnetic field flowing through it, then I'm going to accumulate some magnetic flux. After all, I get flux when a magnetic field goes through a loop. So if I want to calculate the total magnetic field through this solenoid, I know that I'm going to have to take, well, the magnetic field strength, which is mu naught Ni, convert that to a flux by multiplying it or by dotting it with the area vector, but since I'm looking at the magnitude here and the area vector and the magnetic field are in the same direction, I can multiply the two by each other. And so the magnetic field times the area gives me the magnetic flux, but that's just the magnetic flux per turn. So if I want to find out the total magnetic flux, I have to take this and multiply it by the total number of turns in the solenoid. Now, this formula contains two different n's, so let's just make sure that we're on track with which one is which. The big N is just the number of turns in the solenoid, and I get that n by taking the flux per turn and multiplying it by the total number of turns. Whereas the little n is the number of turns per unit length, which is the quantity that I used to derive the formula for how strong the magnetic field was inside the solenoid. Okay? And so one of these is total number of turns, and one of them is the number of turns per unit length. Well, now I have the total flux, and this is a self-flux, right? It's the flux through the solenoid that's actually being generated by the magnetic field through the solenoid, which is being generated by the current that's flowing through the solenoid. But of course, if I have a flux, if I've established that flux, then nature is going to want to keep that flux where it is, regardless of where it came from. And so I can use what I know about magnetic flux and say, well, what happens when I try to change it? So if I go back to my whatever battery I'm using to generate this current, and I try to change the current, well, that's going to try to change the strength of the magnetic field, which is going to try to change the strength of the flux. But I know that Lenz's law and Faraday's law tell me that we don't want to change the flux, right? That this structure itself is going to try to keep that flux from changing. And so solenoids are really interesting because they produce their own EMF when you try to change the current. And I can use Faraday's law to actually come up with exactly what that expression is, because the induced EMF is given by the rate of change of flux. And so I can just plug in what I know for the total flux through this solenoid, and I get a pretty simple expression for what the self-induced EMF is going to be due to this solenoid. And I get something that's actually pretty interesting, because I get some mathematical expression, right? I have a minus sign because, of course, the EMF is going to counter the change in current, right? It's going to counter the change in the magnetic field. But I basically get a relationship that says the amount of EMF, the amount of the self-induced EMF is going to be proportional to how quickly the current is changing. If I try to change the current more quickly, then I'm going to have more self-induced EMF. If I try to change it slower, then that self-induced EMF is going to be smaller. But the constant of proportionality is indeed just that. It's a constant, and it's given by the geometry of the situation. It's given by the properties of the solenoid itself. And so what I found just by looking at a solenoid is that I get a self-induced EMF from an object that's inside of a circuit just by changing trying to change the magnitude of the current. And so this is what we call in circuit dynamics an inductor. Okay, so the term inductor means any object that's going to create a self-induced EMF when I try to change the current. Therefore, there's going to be an EMF, which is proportional to di dt, and that constant of proportionality is what we call L. And that L is what we actually call the inductance. The unit of inductance is the Henry, which we abbreviate as H. And of course, as we derived it for a solenoid, the inductance of an ideal solenoid is actually best measured in inductance per unit length, because that changes the capital N to a little n. But for a solenoid, the inductance per unit length is given by a pretty simple mathematical expression. How I like to think about this is, if I put something like a solenoid into a circuit, it's going to use the properties of the magnetic field to kind of add a little bit of an extra battery whenever I try to change the current, right? And so it's adding something to the circuit to, again, try to slow down the rate of change of the magnetic flux. And how do you slow down the rate of change of the magnetic flux? Well, you slow down the rate of change of the current. How do you do that? Well, you kind of add this time-dependent battery, okay? And so that's how I think about solenoids, or how I think about inductors when I put them into a circuit. Okay, so we can actually do something pretty fun with this, right? So now let's consider a slightly more complex circuit. I have a battery that has some EMF, and then I have it connected to another loop that has both a resistor of resistance R and an inductor with an inductance L. And then there's this switch. And the switch can either be connected to terminal A, in which case the battery, the resistor, and the inductor are all in the same circuit, or it can be connected to terminal B, where I just have the resistor and the inductor in the circuit. Okay, now this should remind you a little bit of when we did LC circuits a couple of weeks ago, and I think probably the math will remind us a little bit more of that later. But for now, what we're going to do is we're going to connect the circuit to terminal A, and now I have a single loop, right? And I can actually apply Kirchhoff's laws. So I'm going to go clockwise around this loop. I'm going to start here on the lower left side, and I'm going to see what happens as I go around the loop. Okay. The first thing that I encounter is the EMF, and so I know that my change in potential, which is going to be equal to 0, is going to be going up by the EMF of the battery. Now, I have to guess, of course, the direction of the current in order to do the rest of it, so I'll guess that the current's going in this direction. Why? Well, I'm going around in that direction. I might as well have a current in that direction. Well, if I is going that way, then the change in potential across the resistor is going to be negative. So I'm going to go down by I times R. And now I hit the inductor, right? And I can easily write down what the magnitude of the change in potential across this inductor is going to be, because I have a definition from what I just told you that the self-induced EMF of an inductor is proportional to L times di dt. But I do have to think about this sign a little bit, right? Because the sign of this EMF is going to be the sign required to fight the changing current, right? It's going to be the sign required to fight the changing magnetic field, to fight the changing magnetic flux. And so in addition to thinking about I going around clockwise, what I like to do is I like to imagine what would happen if I were getting bigger, right? So if the current clockwise through the circuit is getting larger, right, then the inductor will, the inductor will see a larger current, a di dt that's positive, and therefore Lenz's law will try to fight that changing current by putting in a tiny little battery in the opposite direction to try to fight the increase in current. And so I'm going to end up with a minus L times di dt. Now this sign works out if you do the thought experiment the other way. If the current were decreasing, then you would want a little battery that makes the current flow a little bit stronger, right? And so you'd add a little battery that has L di dt. But of course the minus sign gets taken care of, because in that situation di dt is negative. And so I end up with this beautiful and simple mathematical expression for what I get when I go completely around the circuit. And now this is something that we probably recognize, right? Because we saw exactly the same mathematical expression when we looked at LC circuits, right? We have now the variable that we're trying to solve for is the current, but I have a simple differential equation that can help me solve for what the current might look like as a function of time. Okay, let's go through those steps a little bit more slowly. So I have that expression for, I have the expression that I got out of Kirchhoff's laws. I can separate it, so I move everything with a t to the left-hand side. I move everything with an I to the right-hand side. And I get something that I can use a U substitution, or I can directly integrate it. And I get that the current obeys this interesting relationship where I have an exponential, and I have somehow now a natural time constant, which we might call tau, which is L over R, which kind of, which parameterizes how strong the change in current is with respect to time, right? This number, this tau, is the thing that's going to tell me basically, how long is it going to take for the current to build up? How long is it going to take for the current to die down? And I'm going through this a little bit more quickly than I did last time because you've seen this mathematical relationship before. Except there, when I looked at LC circuits, I saw a charge that was building up on the capacitor. Here, I see a current that's building up in the circuit, right? So it's a nice analogy, but the quantity of interest here is the current that's building up, charge that's building up. But if I plot this expression, I see exactly the same thing, right? I see starting it, when I plug in t equals 0, I have no current at all, so I attach the switch to terminal A. Instantaneously, there's no current. Of course, the current wants to move through the circuit. The inductor is fighting that change in current, and so the two things are balancing each other out. Of course, the battery's always going to win, right? Lenz's law slows things down. Faraday's law slows things down, but it doesn't really stop things. And so if I wait long enough, then the current is totally going to build up in the circuit. And that's really interesting because in the same way that I had charge slowly accumulating on the capacitor, now I have current that sort of slowly accumulates in the circuit, right? And this also helps to understand why when we connect things in our real life circuits, there's always something that's a little solenoidy in it, right? And that's why it takes some brief amount of time for the current to come up to its steady state value, right? So that's also kind of interesting. Okay, well now what happens if I take this same thing but I connect it to B? Now I'm thinking about starting this after I've developed a current in the circuit, right? So I've done step A, and now I immediately take the switch and I move it from terminal A to terminal B. Well, now I have something that's a little bit easier, right? I have just two elements in my circuit. Of course, I had assumed before that the current was going this way, so I'll keep the current going that way. And as I go around the circuit, I don't really need to know much about the current other than the assumptions that I put in before, right? So I still, when I cross the resistor, let me start here so that I hit the resistor first. I have minus I times R as the potential across the resistor. And when I hit the inductor, well, I have the same relationship. If that I were getting bigger, then the inductor would act like a little battery opposing the current. If I were getting smaller, it would act like a little battery supporting the current. And so I still have a minus L di dt. Now, the physical setup here, when I move the switch from A to B, of course, I know that I'm starting with a current, and that current is probably going to dissipate away, right? But when I set up Kirchhoff's laws, I don't really care about that current, right? It's always going to be the same relationship between the EMF that's induced on the inductor and the current that's flowing through the circuit. So if I take this and I do the same calculus on it that I did before, I separate it, I move the t's to one side, I move the i's to the other side, and then I integrate both sides, I get out an expression that again isn't a surprise, that my current now looks like a decaying exponential, again where that same time constant appears, right? So t always appears next to r and L, so there's always this natural time constant equal L over R, which parameterizes how strong this system is, right? So both the inductance and the resistance tell me how quickly is the current going to build up, and then how quickly is the current going to dissipate. And if I go to this same chart, well, here I'm starting with the maximum current, and the current is going to dissipate away to zero. The same way that I took my resistor and capacitor, once I disconnected the battery and hooked those two up, the charge dissipated away as a decaying exponential as well, right? I build up current and then I allow the current to dissipate away, right? And it's a beautiful analogy between the circuit that we're looking at here and the RC circuits that we studied last month. Well, what was the last thing we did last month? After we saw this great buildup of charge and then discharge, what we did was we took that system and we said, well, what's really happening inside the capacitor as that charge builds up? And we said, well, as the charge builds up, there's an electric field that's building up, and then there's energy being stored in that electric field, which kind of acts like a battery later. Well, the same thing is probably happening here. But instead of the electric field being built up inside the capacitor, I have a magnetic field that's being built up inside the inductor, right? And then Faraday's law is the thing that is moderating, is controlling how that energy is built up inside the solenoid or inside the inductor, and it's Faraday's law that's telling me how that energy is dissipated. But I can still calculate it, right? So I know that power is equal to I squared times R, right? And so I can plug in the expressions that we developed for how for the power being generated. So I have an R. Let me start at the let me count up all the energy that's released, because that circuit's a little bit easier because there are just two components in it. And so I know that I is equal to I naught, the starting current, times e to the minus t over tau, and that's squared, right? And this is actually a pretty simple mathematical expression, so it's equal to r times I naught squared e to the minus 2 t over tau, right? So I can write down, well, what is the power as a function of time? Therefore, I can integrate that power as a function of time. So it's 0 to infinity of I naught squared r e to the minus 2 t over tau dt. Well, this is an integral that it's pretty easy to do. It's pretty easy to do a u substitution on this, and I get that this is equal to minus r I naught squared tau over 2, and now I have e to the minus 2 t over tau evaluated from 0 to infinity. Evaluating e at e to the minus infinity is really nice. That's just 0. E to the 0 is equal to 1, and so I'm left with r I naught squared tau over 2. Okay, now this is kind of this is a nice expression, but it doesn't really tell me much about how I can reconnect this back to the system that I'm looking at, right? Like, what does this have to do with the physical constructs of the inductor and the resistor? Well, I can recognize inside of this the actual expression for the I can actually recognize the expression for the inductance, because remember, tau is equal to L over R. And so if I plug that in, I get that this expression is actually just 1/2 times the inductance times I naught squared. And so I get that the amount of energy that I've dissipated is proportional to 1/2 I naught squared times the inductance, right? And so the inductance then parameterizes how much energy is stored inside the inductor, which is really just an expression of saying the inductance tells me how much magnetic field is stored inside the inductor. Okay, so here are your take-home messages. Inductors are cool circuit elements, and they're cool circuit elements because they act like little batteries when they have to. When I try to change a current, an inductor uses Faraday's law to try to fight that changing current. And as I charge up an inductor, as I build up current, I'm actually storing energy inside that inductor, which then can be used later to try to stop the current from changing. But really, when I look at that inductor, the energy is being stored inside the magnetic field, and that's an inductor.